So the last thing about normal distribution that we need to know is what we call an approximation to the binomial distribution. So we're going to use this when we have a binomial distribution question or set of information, but the numbers are so huge that it wouldn't make sense for us to use our binomial distribution formula. And rather we can approximate it, and that way we can then use our formula for binomial for mean and variance to then solve something using the normal distribution table instead. So an approximation can only be used if you have your binomial n, which is your total number of samples, times p. Remember, that's the probability of success. And when n times p is greater than 5, and also when n times q, and remember q is our probability of failure, is also greater than 5. So if those are both greater, then we can use our approximation. And the first thing we will do for approximation is you work out your mean and your variance using your binomial formula. So the mean is always n, which is our total number, times p, the probability of success, and the variance is n times p times q, which was our failure. And once we have the mean and the variance, I know that I can then square root that to get my standard deviation. So then I can do my normal distribution where I can standardize my variable and read it off the table. So the only real important thing to remember though, when we're doing approximations, is the formulas for calculating the mean and the variance. But then, whenever I've calculated normal distribution before, if I had a greater than or less than sign, but it was equal to, it doesn't matter. You only ever use the greater than or less than signs. We never added that equals to. But whenever we're calculating binomial distribution and we had a greater than an equal to sign, the equal to part means that something was included. Whereas if I just had the greater than sign, then I didn't include a certain number. So because of that making a difference, what we have to have when we're doing an approximation is what we call a continuity correction. So the continuity correction, it's just a change to our total number whenever we have a difference in signs, because we need to then see what happens when we've got that including with equals to part. So if I have something that is less than, I am going to minus 0.5 from my value of x that I'm looking for. If I have less than or equal to, then I'm going to add 0.5 to it. If it's greater than, I'm going to add 0.5. And if it's greater than or equal to, then I'm going to subtract 0.5. So I do this to each of my x values depending on what I'm looking for as my second step after I've done my mean and my variance calculations, because then, only then, once I've added or subtracted 0.5, can I then standardize my z value. So if we look at some examples of this, so I have a pair of fair coins being thrown repeatedly until a pair of tails is obtained, okay? And then it says on a different occasion, a pair of fair coins is thrown 80 times. Use an approximation to find the probability that a pair of tails is obtained more than 25 times. So I need to check that I can use an approximation. So I say n times p and n times q, okay? And then if it's greater than 5, then I can use it. But now I need to get my p, and the probability of success is getting a pair of fair coins. So that means I am going to have my first one to give me a pair of tails. Okay, and tails, it's going to be a half because there's only one side of the tails on a two-sided coin. And then I'm going to get another tail, so that's another half. And a half times a half gives me a quarter, or 0.25. So there I have P, and I remember Q is going to be 1 minus that, which is going to be 3 over 4, or 0.75. So now I have P and Q, so now I can work out the mean, which is going to be N times P, which in this case, my N is 80 times. So I've got 80 times P, which is my 0.25 or a quarter. And that will give me a mean of 20. Then I've got the variance, which is going to be N times P times Q. So I'm going to say 80 times 0.25 times 0.75 to give me my variance. So now I've got mean and variance, which I remember can work out to standard deviation. And now I can see what I want to solve, because now it says I must find the probability that the pair of tails obtained more than 25 times. Okay, so more than 25 out of 80, what we would have normally done with a binomial distribution is you would have then said 26, 27, 28, all the way up to 80, and that's a lot. So that's why we rather use this approximation to make our sum much easier. So I want the probability that my variable x is obtained more than 25 times. So it's more than, so it's greater than 25. But since I just said more than, I'm not having any equals to, it's just the greater than 25. Okay, so that's all I want. So now when I'm standardizing the variable to find z, it's going to be greater than. I first have to do a continuity correction. So this is just greater than. So if I look, greater than, said I must add 0.5. So I'm going to say 25.5 now, minus the mean of 20, divided by the standard deviation, which is the square root of my variance. And that will then give me a value for z. So I want z greater than 1.42. And now I can solve just like I normally would with my normal distribution, because I would draw my curve and I want where it's greater than. So that means it's everything higher to the right, and it's 1.42, so it's positive. So I want everything there. So that means, since I can only solve to the left, I would say 1 minus my phi value of 1.42. So I'm saying 1 minus, and now I look up by 1.42 on the table. So where we have our table, then we find 1.42 is 0.9222. So then I say 1 minus 0.9222 to get my final answer of 0.0778. Okay, so that's what we would do for an approximation. It's always going to be out of quite a lot of marks, but that's because you need to always find your mean and your variance, as well as do the continuity correction, and all of those things will be assigned marks before you then solve as you would normally for your normal distribution. So if we look at another example. So here I have 70% of adults own a car, and a random sample of 8 adults is chosen, okay, for our first part of our question. But then a random sample of 120 adults is now chosen, Okay, and we need to use an approximation to find the probability that more than 75 of them own a car. So in a binomial distribution, then I would have said 76, 77, 78, all the way up to 120, which is a huge amount. So now, for my approximation, all I'm going to do is I'm going to find the mean of n times p, and n is 120, times the probability of success is that the person owns the car, so that is 70%, which is 0.7, to get a mean value. And then variance is going to be n times p times q, which is 120 times 0.7 times 0.3, to give me a variance value. So now that I have the mean and the variance, now I can work out what I want. So I want the probability for when my x variable is more than 75. So that's greater than 75. Okay, so now it's just more than, so I don't need to include an equals to. Okay, and now when I'm changing to my standard variable, I need to do a continuity correction. So I have a greater than sign. So greater than is add 0.5. So I say 75.5 minus the mean divided by the square root of the variance. And that will then give me a z value . Okay, but now my z value ends up being negative. So I would draw my graph, and I want greater than, which means everything to the right, but it's a negative number. So I want everything over there. And since I can't solve when there's a negative, the first thing I need to do is flip the curve. So if I flip the curve over, and that becomes there, and then I now want that, I would solve as normal because I want everything to the left. So now on my table, I am going to look for my 1.693 to find my value. So I look through my table, I find 1.69, and then 3 is adding 3 onto that. So adding 3 would be my 0.954, and then 5 plus 3, which would give me 8. So I've got 0.9548 as my answer, and that would then be my final answer. Okay, so that is how we solve for an approximation. And if I look at just 2 more examples. So over here, I've got the probability that Moena messages her friend is 0.72. Using an approximation, find the probability that in any period of 100 days, she messages on fewer than 64 days. So I need to work out my mean of n times p, which is 100 times the probability of success is 0.72. So that will give me a mean value. And then the variance is n times p times q, which is 100 times 0.72 times 0.28. And I get a variance value. So now I want where she messages for fewer than 64 days. So that means that my x variable is less than 64. because it's fewer than 64 days. So now I'm going to standardize, and the first thing I need to do is a continuity correction. So now I want where she is less than. So less than means minus 0.5. So now I'm going to say 64 minus 0.5. And that means that I would then end up with 63.5 as my correction, minus the mean, divided by the standard deviation, which is the square root of the variance. And that then gives me a z value of negative 1.893. And now it's less than, so now I'm going to draw my curve. And it's a negative value, so it's on this side, but I want it less than, which means it's everything smaller and to the left, so it's everything there. So now, since it's a negative, I know that I need to flip my curve. So if I flip my curve over, it means I want all of that. But now I can't solve to the right, so I need to say 1 minus everything to the left. So I'm going to say 1 minus my 1.893 from the table. So that is 1 minus, and now I look up 1.893. So on the table, I'm going to find 1.8 over there, 9, and then 3. So 1.893 says add 2 to my last 2 digits, so I have 0.9708. And when I subtract that, my final answer then ends up as that. Oops. It's 0.0292. Okay, for my final answer. So that is another example, but that was a different continuity correction. So the important thing to remember is you have to just learn these of when to subtract and when to add, because it will affect your final answer. So if I look at the very last example that we're going to do, I have the probability that a train arrives late is 0.35, and a random sample of 142 days is taken. Use an approximation to find the probability that the train arrives late on more than 40 days. So I have my n and I have my probability of success, so I can work out the mean of n times p, which is going to be 142 times 0.35 to get a mean value, and the variance is n times p times q, which is 142 times 0.35 times 0.65 to give me my variance value. So now I want my x value of more than 40 days. So that's greater than 40. So now I'm going to standardize. And the first thing, I need to do my continuity correction. So greater than 40, greater than means add 0.5. So now I've got 40.5 minus the mean divided by the standard deviation, which is the square root of the variance. And if I type that in my calculator, I get a z value of negative 1.619. So now I am going to solve using my curve, and I've got a negative value, and I want greater than, which means I want everything to the right because I wanted more than that. So now I know that I'm going to flip my curve, and when I flip my curve, I am simply going to use my value as it is, and I'm going to look that up on the table of 1.619, and 9 says add 9 to my last few digits, so I end up with 0.947 as my answer. And that is how we solve for approximations. So as you can see, we pretty much do exactly the same thing for every single question. The only tricky bit is to remember when to add and when to subtract these 0.5s. And if you can remember that, then it's an easy 5 marks to get in your exam.